Alright, so here's another problem. So a 650 gram block is pulled at a distance of 30 centimeters and released. The period is 1.49 seconds. At what positions does the block have a speed of 0.51 meters per second? So we're given A, that's 30 centimeters. But for the sake of this, since we're in meters per second for the speed, we're going to convert it to 0.3 meters. And then we know the mass, which is 0.65 kilograms. And we know the period, which is 1.496 seconds. So basically, we're trying to find the speed at a certain time. So what I'm going to do is I'm going to use conservation of energy for this. So we we can use the maximum potential energy because we're given amplitude. So 1/2 ka squared equals 1/2 mv squared plus 1/2 kx squared. So I'm going to bring the 1/2 mv squared to the left side. The 1/2s cancel out. And then what I'm going to do is I'm going to divide by k. So you get a squared minus m over k v squared is equal to x squared. So we know that k over m is w squared. So what we got to do is we got to flip it. So we got m over k is equal to 1 over w squared. So a squared minus v squared over w squared equals x squared. And then x is just the square root of a squared minus v squared over w squared. And then I'm gonna rewrite that. So we get x equals square root of a squared minus v squared over w squared. Now I'm gonna plug everything in. So we know that w is just 2 pi over t. So we get x equals 0.3 squared and then minus 0.51 squared over 2 pi over 1.49 squared. So then this is going to give us an answer in meters, but I want to do this in centimeters. So whatever this answer yields, we have to multiply it by 100. So we get an answer of about 27.45 centimeters. Alright, so here we have a slightly different problem. So a 275 gram mass is attached to the spring and then it's pushed 9.5 centimeters and then released. A student found that 10 oscillations take 12.5 seconds, but we're trying to find the spring constant here. So I think the easiest way to do this is to use the formula for a period of a spring. So that's T equals 2 pi times M over K rad. So we know that the frequency is 10 oscillations, 10 cycles, and then over 12.5 seconds. So that means the period must be 12.5 seconds over 10 oscillations. So this is the period of the spring. So what I'm going to do is I'm going to divide by 2 pi. So we get Ts over 2 pi equals rad mk. But this itself actually looks like 1 over angular frequency, because W equals 2 pi over T. So that means 1 over W is basically T over 2 pi. So we could replace this with W, 1 over W at least, equals rad mk. And then we square both sides, we get 1 over W squared equals m over k. So k over W squared equals m, and then k equals m W squared, where W is 2 pi over T. So k equals, and then we have to make sure it's in kilograms, because the units are Newton meters, and that's in kilograms meters per second. So yeah, so 0.275 kilograms times, and then W does equal 2 pi over T, so 2 pi and times, and let's just actually do the frequency instead, because it actually looks a lot easier instead of doing a fraction over a fraction, or no, an integer over a fraction, because that makes things a lot more complex. And then this is squared, so we get a spring constant of around 6.948 newtons per meter. Here we have a multi-part problem. So we're given a mass m, which is 325 grams, and has a frequency of 2 hertz. Initially, it's at 4.5 centimeters and it has a speed of 23 centimeters per second. So we have to find period, angular frequency, amplitude, phase constant, max speed, max acceleration, total energy, and the position at 0.41 seconds. So let's do this from easiest to hardest, which is chronological. So T is equal to the reciprocal of frequency. The frequency is 2 hertz, so that means the period is 1/2 seconds. And then angular frequency is just 2 pi times the frequency, so that's just 4 pi radians per second. Alright. And then the amplitude, that's going to be a little harder to figure out, but we could still figure it out. We just have to use our concepts of conservation of energy. So we're given at t equals 0 the initial value of x and v, so we can use that to our advantage. So we get 1/2 kx squared plus 1/2 mv squared equals 1/2 ka squared. So at t equals 0, the kinetic energy plus potential energy has to equal the maximum potential energy. So we get so then we get 1/2. We get kx squared plus mv squared plus equals ka squared. So we get, and I'm gonna put this a little bit down here. So we get kx squared plus mv squared equals ka squared. So divide k, so we get x squared plus m over k v squared equals a squared. Well, m over k is just 1 over w squared, or omega squared. So x squared plus v squared over omega squared is equal to a squared, and then a is just equal to the square root of x squared plus v squared over w squared. And then when you plug everything in, you should get an answer of about let me see here. You should get an answer of about 4.86 centimeters. So the phase constant. So at t equals 0, x equals 4.5 centimeters. So 4.5 centimeters equals the amplitude, 4.86, times the cosine of v, right? So it should be, so basically it's the arc cosine of 4.5 over 4.86 should be phi, which is about 0.39 rads. Alright, and then the max speed we can figure out using conservation for energy again. So we get, so what I'm going to do is I'm going to actually use the point where it's at max potential and max kinetic. So 1/2, and it's up to you if you want to do the sum of the energies at time equals 0 and set that equal to the max kinetic. That's perfectly fine, but I think it's a lot easier if we just work with less variables. So I'm going to do the max potential equals the max kinetic. So you get 1/2 mv squared equals 1/2 ka squared, and then we get that v equals wa in the end, which is about what's it called, 61 centimeters per second. All right, and then the max acceleration. So we get that k. So we know that k times a is the max force. So force and acceleration are directly related. So when the force is at its maximum, the acceleration is also at its maximum. So we get ma. So k over m times big A amplitude equals a max. But we also know that k over m is w squared. So w squared times amplitude is a max, and then that equals about 767 centimeters per second squared. And then the total energy. So you can do this one or two. We can do this several ways. You can do at ke times 0 plus pe at time 0, or you could do potential energy max, or you can do kinetic energy max. So so up to you. So, but if you do that, it would be 1/2 Ka squared, or 1/2 mv max squared, and then um, 1/2 mv squared plus 1/2 kx squared at times equals 0. Either way, either way you do it, you should get an answer of about 0.0605 joules. And remember that joules is measured in Newton times meters. So make sure to convert all of your all of the centimeters and kilograms, and I mean all of the grams and centimeters into kilograms and meters. And then last but not least, we have x at 0.41 seconds. So we just use this equation, x of 0.41 equals the amplitude, so that's 4.86 times cosine. Here I could here I'll rewrite this. So x of 0.41 is equal to 4.86 times the cosine of omega times 0.41, and then plus the phase constant, which I believe is 0.39. And then the angular frequency is just 4 pi. So we get x equals 0.41, x of 0.41 equals 4.86, and then cosine 4 pi times 0.41 plus 0.39. And then you should get an answer of about 3.57 centimeters.